All right. So as we continue in rotational motion today, we're going to focus in on torque a little bit more, and we're going to focus in on inertial rotation or rotational inertia, or moment of inertia or angular inertia, all those synonyms. We're going to focus in on that quite a bit more and solve a couple problems using both the concepts of torque and inertia. But a couple of reminders before we jump into that. The Unit 15 assessment on positive physics is due next Tuesday night. And so if you have some questions, we'll be kind of going over some torque problems again on Tuesday, just for more practice. But that will be due Tuesday night. And then I'm actually considering moving the Unit 16 one. I need to think about it a little bit, look at the schedule. I might move that to the next Monday, even though that Monday will be starting a new content. Some of the material we may still be learning next Thursday. And so to have it do that night, maybe pushing it a bit. So I will probably slide that one more class day, even though we will still be finishing that day. But the 15 is still due next Tuesday. It's on torque, and we started it last time. We're going to continue it today. We'll kind of practice on next Tuesday, but it's not really anything new to cover for torque after today. It'll just be practicing problems, so which is what positive physics is designed to do. In terms of the AP test schedule, just a reminder, keep your eye out for emails from Mr. Lindsay and Miss Davis. I don't know when exactly they'll send out the information about testing, but keep your eye out for those emails when they come. I won't know because I don't usually get a copy of it, but so keep looking for that. It'll probably be from either Mr. Lindsay or Miss Davis. I did find out that as I think it was either the last time we had class later that day, or it might have even been the day after, I got an email from College Board, and they gave a little more detail. And they said that for the online test, which is the June 9th version, I didn't tell you this part, did I? Because I don't think I knew it Monday. Yeah, so it's a little different, and some of the details weren't given, at least not on the part that I found, both in the email and on the website. But there's going to be as normal, a 50 question multiple choice portion. And I assume that'll be 90 minutes as is on the normal written test. But then on the normal test, it's then 5 FRQs, 3 short ones and 2 long ones. And you get 90 minutes for that. So it's 90 minutes for the multiple choice, 90 minutes for the free response, 50%, 50%, they weigh in for your grade. But on June 9th, it's going to be 50 multiple choice in segment 1. And then a separate segment of 25 more multiple choice, and then only 2 FRQs. So it wasn't really clear the timing on that second segment and the FRQs, if it would be like 45 and 45 minutes, and whether it would be those 2 combined would be the 50% compared to the 50% of the other 50. Some of that was a little unclear. So I'm sure they'll be sending out more information, but it will actually be not like last year. So if you heard last year, the whole test was reduced to 3 FRQs. And this year, they didn't have any multiple choice at all, nothing. They really shrunk it down because of the COVID, and it was kind of crisis mode. This year, it's going to be normal length, but format will be a bit different. So the downside of just the 2 FRQ part, if you don't like FRQs, it can sound pretty good, but if you don't know one of them very well, then you might miss half the points just by not knowing one of them. Whereas if there's 5 of them and you don't know one very well, you could still get 80% of the points on the other 4. So you're pushing the limits or pushing your luck a little bit, I guess, in that regard, but it won't carry the same weight either, I'm assuming, although that wasn't clear on the site. But I'm assuming since there's only 2, it won't carry as much weight, which is logical, but wasn't explicit. So
are the FRQ, so like since there's 2 FRQs, are they still going to be 50% each?
I'm assuming not. That part wasn't clear, how they're weighted and what their points would be. I'm assuming there'll be 2 long ones, but it's an assumption. And it did say that one of them would be quantitative analysis, basically, using whether it actually gives you numbers or you just do it with equations. It's basically asking you to do some calculation analysis. Or I'm not sure why that thing's having a hard time finding me today. I don't think I've got it. Yeah.
So I kind of
let's see.
a bunch of multiple choice.
There we go.
2 FRQ.
Reset the setting. But the I lost my train of thought there with that distraction, so I wasn't on there. Oh, so I don't think it'll be still 50% of your test. I think it'll be different. But one of them will be still quantitative reasoning, and one of them will be a paragraph length response type question. And normally in the 5, one of them is quantitative reasoning, one of them is paragraph length response, one of them is lab based. And then the other two can be anything. They could still have lab components. They still could have quantitative reasoning, but there's always one paragraph linked response, always one quantitative reasoning, always one lab-based question in the 5. For this new online one, the 2 will be quantitative reasoning and paragraph linked response. So again, I'm sure they'll be giving more details. There will be an online simulation test starting in April sometime. So by the time we're wrapping things up and starting to review a lot, there should be a nice online resource for you to practice with, but that won't be available till April. So, and then as we were talking before I started the recording, tomorrow is when the portal opens for scheduling your classes for next year for non-seniors. So if you need some recommendations, I'll probably tonight go through whoever's filled it in by today and get those put in. And then I don't know if I'll have time tomorrow to do more, but if not tomorrow, sometime on the weekend, I'll do the ones that don't get done tonight. So if you need a recommendation for a science class, you can fill out that form linked on the bulletin board page of Access. I did put the information about the test for AP. I did copy and paste a bunch of it off of what I received into that news item on bulletin board. So if you go to Access to the bulletin board page, the news item that it used to just have the dates on it, it still has the dates, but down below that I pasted in what they said about the test. So you can read for yourself if you'd like to see that. All right, any questions about any of that? All right, well, let's go ahead and review a little bit with some problems. So before we go into torque and inertia, I do want to give one more chance to practice angular movement. So from worksheet 1 again, so we're going to go back to worksheet 1, but we're not going to do any of the graphing this time. We're going to actually do the word problems. It's a very common skill that you're tested in multiple ways on the exam. So I want to make sure you feel pretty confident with it. So worksheet 1, the last page, it's questions 7 through 14. We've got 3 of you in the Zoom today. So we'll have you guys, we'll do question number 7 because it conveniently has 3 parts. Okay, so you guys will be in charge of question number 7 on worksheet 1. It's the one that says the Earth spins on its axis once a day and orbits the sun once a year, and blah, blah, blah. So that's your question. As you solve it together, you'll also want to discuss how you're going to display it visually on the screen so that we can all see it. And then for you guys in the class, we'll just go 2, 2, 2, 2. So you two over there, Jack and Johnny, you guys will be responsible for number 8. And then here, Andy and Evan, you guys will be responsible for number 9. You have so 8 is the Ferris wheel question, 9 is the gymnast question. Kyle and Nat, you guys will have number 10. So you've got the wind turbine question. And then Ethan and Kate, you guys have question 13.
Oh,
okay. So it's the one about the bucket in the well. All right.
Yeah.
Does everybody understand the question to do? All right, I'll go ahead and put you guys in a breakout room for the virtual crew. Good luck. And how about 12, 15 minutes, somewhere in that time frame to figure it out and figure out how you're going to teach and display.
we know that much.
For displaying it here in the classroom, I actually will open up this file. And so here is question 7, and you'll just be able to come up here, turn on the marker and draw it right here on the board. Okay, so that way I can share the screen. It'll be easier for them to see in the virtual group.
Okay. Still basically.
So whenever you're done with your question, let me know and I can open this up for you to come up and use it.
Right the answer and then walk back.
Yes, sir. Yes, sir. It's all mental. Mental math.
That doesn't fit in class.
Oh, man. Hey, if half of the thing is, what's it called? Multiple choice. I think that is kind of does work a little bit. That's true. That is true.
That'd be cool if they just gave us the answer, so we could
Bro,
check our work.
how
on
hype
it.
would that be? It's like, hey, just in case you guys want to check your questions, I put all the answers on the back. It's like a 1 through 50. Yes, I think it's just. And
We have, the last thing.
calculator.
There's angular velocity and angular.
I don't feel like calculating.
What's the last?
What's the last I must?
You know, that's the
Okay.
equation we use, but you know what the.
This is what I think it is. It's just,
I think it's
no, that's not that. That's the thing.
0.125 seconds. That's just.
What is?
This is just like-
Okay, I got 0.6 seconds. How do we turn that into
I'm either
0.25?
thinking
Hmm.
distance or displacement.
Divide by,
Hold on, let me make sure this.
multiply by 0 and add
don't get
0.1.
Oh, that's convenient.
So,
0.25 divided by 3.
Um,
Oh, okay, I'm getting closer.
I think we divide them or something. I don't
yeah.
know,
Use this
divide
equation, right?
acceleration.
So
velocity,
the initial velocity.
We don't have any.
Is x equals. Equation for the initial velocity.
Oh, I'm getting close. I got 0.3.
If you guys ever need print copies of the AP formula list, I just try to keep a supply of paper ones, and if you take one, you can just keep it. They're just here in this bottom shelf.
Thank you.
You can send it.
You know the equation?
So, I think it's just the thing that was happening.
Find acceleration.
Also pi. Yeah. So in the end.
We have to find revolutions a second.
Which is
Well,
operating speed.
I don't remember the equations.
Hmm.
Isn't it just the kinematics equations with like different variables?
Oh, yeah, the WEWAT or something like that.
Yeah, well, I was trying to use this one, but we don't really know.
I
I know the acceleration.
No.
That's the answer.
No idea what that is.
Five
Hmm.
point two goes from
On
on 3 so it increases to.
Oh, okay.
Faster.
So you would say divide.
Yeah, sure. All you have to do, they're on the same graph.
So we have to
Yeah.
Acceleration.
Yeah.
And that gives us what equation you're trying to use?
And then we need to find the normal
that's
force of the AC with the 80 kilogram per minute.
Is that what we should use?
Okay.
So.
Wait, we don't
Well,
need to find
you can use that,
acceleration.
but you're gonna have to do some substitutions because you don't know the acceleration, I don't know the time.
B
But
squared over R.
if you plug in the equation for acceleration for
Well, we don't
for alpha.
have
Oh, yeah.
So
Yeah,
if you plug the equation for alpha in for that, you change it omega over t. And then you don't actually have the alpha in the equation, you just have your omega over t.
Okay.
Does that make sense?
Yeah.
Because alpha equals change in omega over t, so just substitute that in for the alpha.
So
And then you're basically making a new form of that equation.
it'd be like,
I think to find the radius, we can. do
Delta omega, yeah.
B squared divided by acceleration.
Yeah.
No, times t squared, right?
Equals.
So
V
point
squared.
No, it's-
Squared divided.
The
by
acceleration is,
Yeah.
yeah, the acceleration is just, yeah.
2.88 is the radius. If we square the.
Yeah.
Cancel.
So that's
yeah.
velocity over acceleration, velocity squared over acceleration.
So just.
Yeah.
Okay. So that's 2.88 and that's meters.
Yeah, and so
WT.
WT plus 1.
now we just do V squared over two
Yeah, let's
point
go
eight
together.
eight, so 0.24 squared divided by
We
two
get,
point.
So it's
Remember,
WT
it's
plus one
W,
times WT
it's not just
squared.
WT though, it's delta WT, right? So delta W.
No, that
Oh,
doesn't
the-
make sense.
Because it's a change in velocity, not just the
No
velocity.
problem.
Okay, so we can't just combine them.
Yeah.
So
Ding.
how long does it take to really?
Right, the change in velocity.
Maybe times the mass?
Yeah, so if we.
For which part?
I think we have enough to.
Yeah,
So-
that's what I got.
And if you.
How long does it take
This-
to really
this
come up?
Is meters.
Wait, it says the seat,
Yes.
which.
Wait.
1 meter.
I got
Oh,
it.
they give us the
Very
radius.
close.
I-
Point two
It's-
four squared
it's a sig
divided by
fig. It's a sig fig. It works. It's just a sig fig.
Divide the circumference by
Times
meters per
the-
second.
Let's go.
A little confused on part C.
Okay, so you figured out A and B?
More space.
Yeah.
Okay.
Just a second.
Actually, there is not that much room.
Wait, we have,
Okay,
Interesting.
so
we can do, net force.
if you-
and A.
Okay.
did you find the omega,
Last time,
Number of rotations.
Okay.
the
B
W?
Times
This one.
0.02.
That's part B, right?
We're just saying it starts at 0, so I'm not
Or
gonna.
do we
Mhm.
only?
So the
A
tangential velocity, the
Yeah,
V,
try 1/2.
is equal to the radius
Oh, here.
times the omega.
GT.
V equals R omega, V equals RW.
So you don't have acceleration.
Period.
So you get
Two IR.
this.
That one's not on the list that they give you, but that's one of the ones we had in class.
And then
Does that ring a bell? That V equals RW?
Mm,
You use that for part C, because you already found W, right?
So you get
Mhm.
Yep, and they give you the R in the equation, or in the question, I think, right? Is that my remember?
Yeah.
correctly? Yeah, you should be
so
good to go there.
then you have this.
Okay. Thank you.
You're welcome.
Interesting.
20 meters.
If I put 0.12 on positive physics, I get it right. Just say.
Alright, we get this, and then we just plug in all those. Wait, we know the. So we get
What was the equation for normal force?
Wait, this is in radians, right? The
Normal
theta's in
force
radians.
equals.
Did they give it to you in
acceleration.
radians?
They gave it in 1/2 rotation.
So
No,
rotations
it's
aren't radians.
MV
Okay, so just
squared over R,
25.
or just
So,
V squared
well,
over R.
It needs to be in radians, so.
Um,
Oh, for the equation.
Yeah.
So then that's pi. Right?
8.
Yeah.
Interesting.
Oh.
The metal things.
Oh, wait, but it's in revolutions per second.
I have my calculator, someone.
So wait, don't we have to convert revolutions to seconds or something?
3 revolutions per second is 6 pi radians per second.
Right.
Oh, man.
How's it coming over here with you guys?
Now this is a lot of
We're
damage.
struggling to find
And
the
then the
normal
change
force.
is.
Okay.
yeah.
I thought
So
this
actually,
problem was
you
just gonna be
have
like
the
5
fair
divided
view,
by
okay.
3 or
Yeah.
something.
Did you already get part A then?
Yeah, we
Yeah.
got the time.
Okay.
Radians.
So if you think about the Ferris wheel going in a circle, it's asking at the top, right? Yeah.
Yeah.
So at the top, they'll feel a little bit lighter, right? The normal force will be a little bit less than the weight.
Okay.
So if you make your free body diagram, you'll know the weight, because you can just find that M times G. And then the net force will be centripetal. And centripetal is mv squared over r.
Yeah.
So if you find the net force using the idea that it is centripetal, and you find the weight, then you can use your free body diagram. to go, oh, if I know the net is this and the weight is that, what's the normal? Because the net has to be the difference
But
between
I
the two,
guess
right?
it like.
Right, yeah,
Yes.
So that's getting that free body diagram put together. should help.
thank you.
Yeah.
That is immensely satisfying.
How are you guys
Wait,
doing?
so
Hey.
Multiplied those.
Wait.
together and got
9.1 is 758.8.
In the
So
values
then
from
if we
the question.
do,
You guys have the
Yeah.
well.
Yeah.
Okay. Have you figured it out?
Angular
Okay? Yeah.
velocity
All
is
right.
3
So that one is
revolutions per
easy,
second.
not
I thought it was
bad.
6.
Yeah,
actually, there's a little
That's how
thing
you
you
Yeah,
have
you
to
just
set.
have to click it, but once you get it, it's just like, oh, you just plug it
And
into the
then
equation.
change
Yeah,
the-
V equals R omega, V equals R omega.
How
It's
it's
like
going
simple
to
math.
this from
Four
3 to 5
squares.
is 2 revolutions per second.
Over
4 to 5
20.
radians per second.
Yeah, you can do that.
Yeah. And then we had 1/2 rotation, which is pi radians, and then it's just kind of simplifies that.
Yes, sir. I thought it was just gonna
Alright,
be.
you're gonna
I
write
mean-
this on the
Oh,
board.
yeah. 'cause
Uh-huh.
that's angular.
Wait, you're gonna
That
write
was
this on the board.
You want me to?
Initial angular velocity.
I mean, I'll write it if you want.
That's a better way to do it. than what we did.
Let's see. So they give you.
I still can't believe I basically got the answer by just dividing 3 by squaring 5.
Final.
Like literally.
Well,
0.12.
0.125 is 1/8. So.
This would be your theta, but you have to convert it to radians.
That's true.
Oh, wait, that's what we did.
Divide 1 by 8.
You just have to multiply that by 2 pi, and that would be your theta.
Yo.
You know the delta theta.
We just divide 1 by 8.
You know.
We just divided 1 by 8.
One
Easy
by-
dubs.
one by
Yeah, we
eight
did
is
that.
Easy dubs.
Yeah, so we divided the velocity.
So we took 3 and we turned that into a 1.
Yeah.
And we took 5
Oh, no, wait,
and we turned that into an 8 because like that's kind of how
we
math
did
works
something
sometimes.
else.
You just kind of like,
I
you know,
just
what I mean,
found
like,
the net.
and I was like, yeah, I know.
So then we're like, yeah, so we just divided 1 by 8.
I mean,
and
most
then
ways
I got the
work.
answer 1.25.
One
Any
question
questions?
you
It's
just
like,
find
no, that was
out.
an excellent.
Yeah.
Oh, I didn't get that.
That's
fine.
We did.
Two of them are on
For the.
the
Oh,
list,
man.
so you don't have a copy, you can grab a copy over there and just keep it.
So-
Or copies of the bottom.
Hey, Mr. Rudd.
Yeah.
T equals R omega, I realized we
And
didn't
then
use that.
after
Oh,
that,
yeah,
it's just 2
we
weeks
did
of
it.
school,
So.
and we
we
got
had
Friday
the,
off, and then it's Easter break.
Diameter
Uh-huh.
and the speed, so you equals 2 pi r.
Makes sense.
They are.
And then we.
It's the
There were
second
no
semester.
breaks on the period.
Oh,
That plugged it into the
I miss
other
wellness,
one.
but like
Uh-huh.
they were so like literally yesterday. It was so nice that Wednesday off.
The 2 pi is divided out with the radius.
Yeah, it's kind of, it is too much.
Yeah, I haven't seen a final, so it
80 hours.
doesn't give it to us.
At 80 minutes, every class, every day,
I think,
Even if you're not online, it's too much.
it's still too
here.
It's too much of one side.
So
You need
know
like,
that
right,
they eat
because I
You need like a little
and
perfectly balanced is all big shit.
Okay,
yeah, I
So
like, I like
saying
the,
you use this
what we
equation.
had last year in school, the 6-day rotation better than the block schedule.
Okay, so I like that.
It was confusing, but
The final speed,
Mhm.
not the initial.
It was
Start.
Okay, it was nice.
So you'll actually probably want to use the third.
Now
max
I get out after
but
first
convert it
tomorrow,
into angular.
so I can't really
They've
complain.
done 1 and 2 for you, but you can still do the same thing.
I have
So
two
just take
periods
that
off.
omega,
So I get out after
and then your
first.
delta.
That's
theta.
really nice.
So then you
Yeah.
don't need.
So like,
Wait,
you
you only
need
have
to
one
find that
period.
final omega there.
Oh, that's actually.
So you
because
know,
the classes that I wanted to take,
So you
like
can
first and
third
second
and
semester, they all like
Yeah.
clash.
the way to go about it.
Because like there's not enough room in all of the classes, so I had to move like all of my classes.
You guys
to get
finished
the
it
ones that I wanted.
Yeah.
Yes, sir. So
Okay.
basically, we took the 3 and we turned that into a 1,
Hmm.
and then we took the 5 and then we turned that into an 8, and then we divided it, and then we got the answer.
Yeah, we worked backwards from the answer.
Can you explain it?
No, we were joking. We had.
Okay, as long as you can explain it. So which one did you?
So
go
we
for?
got the answer out of
Yeah, no,
math.
Answer.
And
I looked at the answer sheet.
dude, that's like when you do mental math on the test and you write the answer and then you're like, oh wait, they won't work. And so you just go through the rest of the problem.
All right, so you guys have number 9, right?
Yeah.
Yeah, so you guys can go ahead and start putting your work up while we're waiting for others to finish.
We're still.
Yes, sir.
Lost on how to do it.
No.
I'm not sure if we're using the wrong values,
We're
because we've
almost
tried
back.
multiplying, and dividing every which way using the formulas, and it still hasn't worked.
What are you coming up with?
We're coming up with like depth, very small,
Oh,
2-point decimals.
do you have a free body diagram drawn somewhere with your courses?
No.
Okay,
That's a nice one.
Yeah.
start there.
Bro, okay.
And you don't even need the circle part, like just draw the person.
Oh, yes, my favorite
dot.
integer, the
The
fish.
weight would be down.
The
Normal would be
fish.
up. Right, and you know the weight. And you know the net, did you find the centrifugal force, the MV squared over R?
Yeah, we got a strange answer to that too. I'm not.
How can I erase that?
I think if you just like, oh, you see up there's like that thing. Look here. No. Wait, maybe. No, this is thing.
I
Wait,
keep getting.
never mind, it is that.
0.2304.
Yeah, there we go.
So you're using
Does that work?
V squared.
Nice.
Okay, so
I
I don't wanna write the whole thing out.
Oh, that's not for
Yeah. Once the pair.
I think you could just simplify it from there, like just.
yeah, I'm just gonna put up simplified.
Yeah.
And the radius is 20 meters, so you'd be, V squared would be 0.24 squared over 20 meters. It looks like you're doing that there, but why did you make it 0.02?
Oh, that was for the time and the first dollars.
Oh, okay, that's a different word, okay. So if you take that V squared, 0.24 squared over the 20, that's your acceleration. Times the mass of the person, 80. That should give you the centripetal force that they're feeling, which would be the difference between these two.
Yes.
Yeah.
Oh, yeah,
Look at that handwriting.
absolutely.
So 0.24 squared
Flawless.
times 80
I kind of skipped a couple
divided by
steps.
20.
Yeah.
It's okay, I don't think
So
anyone
you're-
will let you get out.
No,
No,
it's
I'm gonna, no one's gonna fight
0.2304.
out.
Actually, Are you guys done with yours?
Yeah, we are.
Okay, let's have you go ahead and start putting yours up.
I'm in ready.
What's
I
think
I haven't got it.
Okay.
Oh, well.
Working on it right now.
Well. Very nice.
Oh, that's.
Oh, sorry, this is not V.
I
This
thought
is
you were drawing a
I.
face for a second.
How you
writing?
You actually have to convert it. to V.
Oh, yes, sir.
Remember, V is R times omega,
Oh, so rate to 20 times. 0.2.
then that's your V, because the V
Okay.
has to be the linear velocity.
So 4.8.
So go ahead and close
So
it up.
I
Right,
did
yeah.
just 20 times.
Right, I forgot about-
0.4.
I feel like we're having everyone here, you kind of forget about
And
Zoom.
what is that? 4.0?
Yeah.
4.8.
Like,
And then, so if you do 4.8.
because it's like, there's no like, I don't know how to explain it.
Do 4.8 squared divided by 20.
Yeah, you do 80 times 4.8 squared over.
Yeah, I gotta remember tomorrow. And like.
Oh, yeah.
Everyone was supposed to be there, so I was thinking, oh. who's
That was
absent?
tough for Nico.
And I was like, he did, actually, I talked to him since then, he was absent, so
Oh.
it was fine, but.
That would have been really bad. He was trying to get.
But I was
us
just-
the entire time.
I was just thinking
Oh,
that
sorry,
there's an eraser at the top.
92.16.
Okay,
Yeah. same.
I know that some of them, when you like stick your whole hand on it, it'll erase.
Yeah.
But I think it's a different.
So then
Um, yeah, so it turned out fine, but yeah, I was thinking, oh,
so
he's
is
just
this,
absent.
what is
he's
this
supposed
value
to be
meant to
here?
be?
And then I realized, oh yeah, they
That's
are
supposed to be
allowing
null
students
for
still
us.
to make that choice.
Yeah.
Well, yeah, a bunch of people like.
Did we
said they were
convert
coming
correctly?
and then didn't come.
Yeah,
I don't know if it was because it was like, I
So,
think I'm coming.
yeah. Well, this morning, Monday, I had 8 people.
Yeah, we did
got
it. We
6
just did.
people.
We did.
And
42
today,
people.
4 of
Over
them, 2 of them came on virtual.
Yeah.
So they came Monday, but then
No, that
today
doesn't-
they
that
didn't,
doesn't
they
make
just
sense
did virtual. So
either.
I was like, oh, I
Oh.
expected them to be
It
here, but
doesn't,
then they weren't. So yeah, I just have to turn on Zoom every time, whether I expect people to be there or not, I guess.
No, it doesn't.
Hard in the fractions, but the pi cancels out later.
Hard in
So I'm
the
gonna
French.
keep it.
Like your smiley face picture over there.
Yes, it had to be done.
It adds lore to the well.
So then you do.
All right, welcome back from your breakout groups. We just have one of the groups putting their work up on the screen here. And we'll have you guys do a share screen. You guys have the first question, so in just a few minutes, as soon as he's done writing, we'll have you do the share screen and get us rolling with question number 7.
And then algebra.
Explaining stuff over Zoom is so hard.
It is.
So that's
So Kyle and Nat, have you figured it out? Now that you have those equations?
Yeah, we got it.
Yeah.
Trackpad like
Right now. All right, good.
Well,
And then
if I'm being
Jack
honest, my
and Johnny, are you
trackpad
guys?
isn't that
No,
bad.
so when we
Mine is so
converted
bad.
it, we still got,
I used to have a game with the
we
trackpad,
got,
but I didn't have a mouse.
after converting.
And
it,
I was
that
on a
just ended up
Mac,
like
so I couldn't really fit that.
92.6. Okay.
That's the net.
Cause
force.
I was more of a console.
Okay, now you
Computer.
make sure that I did that.
So like
The
anytime.
net
I-
force is the difference between them, so 800
I got
minus
figured.
X.
No, no,
Yeah,
no.
nine.
Oh, okay, so.
Actually, I did play League of Legends for a while with the trackpad.
And you use 10, right?
It's-
For G?
It's hard.
I use 9.81.
Oh, you did? Okay.
And then I
So
got a
that
mouse
is
that didn't work, so it's
700.
like.
Well, no,
Okay,
you must not, because that's 800.
So my mouse,
It would-
like, I
it wouldn't be-
Oh, right.
Yeah, it's okay if you do.
It would
10.
move
That
on
just
its
means
own.
your entry's gonna be a little bit different.
It would like
Okay,
shape,
so
and it
that's-
wouldn't even
that's
be
right.
V
Here
shape.
it says 90.
Cause like literally, I would just hold my mouse like this, and then it would go like this.
Oh, that's.
So I can.
And then I
Right,
like I
so-
changed the clicks.
So after you
like
get
I
the.
changed
Alright,
something in my
so-
settings and I fixed it.
Yeah, there we go. So once you get the 92.
For,
Uh,
for each
do
group,
80 times 9.81.
whether you're
which is
in the
700,
virtual group
which
or
is
in the
12.
class, do give us some context about the question, because not everyone is necessary. The other groups haven't read your question, so rather than expecting them to try to read it while you're explaining it, just give a little context when you're giving your explanation of what your question's asking. Because unlike a lot of times with assignments, everyone's done all the same problems, you're showing your solution. Most of the groups haven't even read your question yet, so we're gonna actually start with number 7 though, Ethan. So even though you just wrote yours, we'll do them in numerical order. So so when you get your problem, have someone kind of introduce what the question's about before you show.
Yo,
it.
it does.
What?
The V looks like a nose.
All right, so for
Nice.
first group, you guys have number 7. If you guys want to hit share screen or how you're gonna show your work.
Can you put up a whiteboard so we can just draw on it or write on it?
Left side of both eyes. Gosh.
Yes, the track pad drawing.
Will it let you draw it?
Yeah. He was like.
No, I don't think it's letting us annotate.
Okay.
If
So
someone else wants to go, I can write out the work and then share.
Well, if you just click share screen, you can set your own whiteboard.
You got me.
He's looking at all of us.
There you go.
Is it working? Okay. Okay, so for number 7A, it's asking the angular velocity of Earth as it spins on its axis once a day. So one rotation, which is once a day, is going to be 2 pi radians, and that's over 86,400 seconds, because that's how many seconds are in a day, and then that gives you 7.27 times 10 to the -5 radians per second.
Okay, then for part B, it's asking for the angular velocity as Earth spins, as it orbits around the sun. And so it orbits once a year. So it would be the angular displacement over change in time. So it'd still be 2 pi radians over 365 days. And then to convert that, you would do a day over 24 hours to cancel out the days. And then times that by an hour per 3,600 seconds to cancel those out, to cancel the hours out. So then that would equal 1.99 times 10 to the -7 radians per second.
Doesn't want to let you.
Okay,
I don't know.
okay, so then for C, we're trying to find the tangential speed with the respect of Earth's axis rotation of someone standing on the equator. So that equation is like, it's B equals RW. And so I put in for the radius of Earth, it's 6.37 times 10 to the 6th power. And then for W would be 7.27 times 10 to the -5. We used which we got from the first question, which would then be 463.
In your units on that last one.
Oh, it's sorry.
I think if you go up to the tools and click on the arrow again instead of the letter, it might let you stretch those. Not sure though.
Wait. Oh, there we go. Okay, yeah.
All right, very nice. Leave that up there just for a little bit so people can glance it over. Any questions about part number 7? First 2 are pretty much dimensional analysis kind of questions. And then part C is using one of those equations that College Board doesn't tell you, but we've mentioned a few times now that's pretty helpful, that B equals R omega. So
How would sig fig work?
I think actually on this one for sig figs, I think probably the way they've written it is more accurate, because I think all the numbers they gave are accurate to 3 sig figs. So I think what they have on the board is better than the key. They probably just didn't put their answers in sig figs on the key. This is from the New Jersey Center for Teaching and Learning, so. I could probably go ahead and edit though. I'll check that. Any questions on 7? We good with that one? All right, nicely done. Thank you, group 1. And now let me share the screen for this group. A couple of the groups had a head start, so they already have put their work up on here. Most of the groups have not. So I'm going to minimize your pictures. Actually, just put it at the bottom. That'll probably be out of their way. So we'll hear from the next group talking about the Ferris wheel question. So again, give us a little context. What's the question asking about? And then how did you find it?
Okay, so there's 2 parts to this question.
Oh, sorry, before you start, you don't need that pen. You can close that because that freezes the screen. It's up at the top. See where the markers are? It's already selected.
Oh, so we're,
Yeah, so you're good to go. You can change the color if you want, but.
so there's 2 parts to this question. So we're dealing with a Ferris wheel that rotates at an angular velocity of 0.24 radians per second. And starting from rest, it reaches its operating speed with an average angular acceleration of 0.020 radians per second squared. So the first part that they ask us is how long does the wheel take to come up to operating speed? So we did this by simply dividing our angular velocity, which was 0.24 radians per second, over our angular acceleration, which is the average, which was 0.02 radians per second squared. And that would equal to a time of 12 seconds exactly. So that's how long it takes the Ferris wheel to get up to operating speed. And then I guess I can start off part B and then you can finish it. So part B then asks, once the Ferris wheel reaches operating speed, what will be the normal force by the seat on an 80 kilogram person at the top of the Ferris wheel? And then it also tells us that the seat which the person sits is located 20 meters from the center of the wheel. So 20 meters would be our radius. So we drew a free body diagram. So the dot is just the person. And then that's a normal force. And this is the force of gravity. And so the mass of the person in the chair is 80 kilograms. But then once we multiply that, we did 9.81 to be more exact, like the answer at the bottom. So then that would give us the force of gravity of 748.8, and then we did sig figs once we, yeah. And then, so from there, we need to go back to this, since they're both in radians, we converted them by multiplying the 20, which is our radius, times 0.24 to get 4.8. And this would be meters per second, right? Yeah, so 4.8 meters per second. And then do you want
Yeah, I
to
can
do
do
the
that.
rest?
So now that we have velocity, then you just do the mass, which is 80, and then you do times the velocity, so 4.8 squared. And then over the radius, which is 20, and then you get 92.16. And then you just subtract that from 784, and then you get, let's see, our answer was 692, and then the key says 690, but yeah.
Yeah, there's 3 sig figs, so it rounds to 690 newtons.
Let's go 690. That looks so bad, but
Well, they can see the answer on the key
Got
here, so, yeah, good. A few things that I would add in terms of, I'm thinking not, you guys explained it well, but in thinking in terms of how the rubric normally scores. So you guys can take a seat now. I'm just gonna add some details that they're gonna probably look for. So what you've done here is basically said that omega, or change in omega over alpha equals time.
Yeah.
And so they would want that equation, whether you write it that way or whether you write it alpha equals change in omega over time. That's kind of the standard. Whichever way you write it, you need to write it some way. And then here you set it, but you would need to have that centripetal force is mv squared over r. So just on the test, making sure that you include the equation itself, not just the numbers, to make it really clear. So those would be the two things I would say. Most likely you would have to add to earn full credit on the AP exam because they always expect you to show what equation is it, not just go straight to the numbers. So you said it as you were doing it, but just a matter of making sure you're well prepared for that exam. So any questions on number 8? All right. Number 9, I believe, is already written, so you guys can come up and just give us your explanation.
Sure. Okay, I'll do it from like.
Give us some context what the question is talking about too.
Oh, yes. I got you with the context. All right. So the context, a gymnast is performing a floor routine in a tumbling run. She's spinning through the air, increasing her angular velocity from 3 revolutions a second to 5 revolutions a second while rotating through 1/2 of a revolution. And we have to find the time on how much 1 revolution takes.
Yeah, so we used the equation, it's like the second kinematics equation in angular form, I guess. And then we plugged in change in what's the W over time for the acceleration. And we rearranged it to solve for time. And then we plugged in, well, we had to convert from revolutions per second to radians per second. And we had 1/2 a revolution, so that's just pi radians. We plugged it all in and it simplified to 0.125 seconds.
Yes.
Can you clarify, how did you convert the revolutions per second to radians per second?
We multiplied by 2 pi.
Yes.
So yeah, you can't plug in your angular velocities as revolutions. It does have to be in radians. So, but we know that every revolution is 2 pi radians. So you can just multiply by 2 pi to change it, which they did. Questions on number 9? All right.
Okie dokie.
Number 10.
Let's go.
So the context for ours is there's a wind turbine spinning with a constant angular speed, and it has, as it's spinning, it has a gradual acceleration of 0.140 rads per second squared. And after making 2,870 revolutions, its angular speed is 137 rads per second. So for part A, it's what is the initial angular velocity of the turbine? And we used, well, first we converted from the 2,870 rev. We converted that to rad, so it's 18,032.7 rad. And then we used, I believe, I could be wrong on the number, I believe it's the third kinematics equation, where it's the final angular speed squared equals the initial angular speed plus 2 angular acceleration times the angle. And then, so when we plug that in, so it'd be sorry.
There's an eraser up there, just a few over from the markers. The
It's
markers
like the
are
first
highlighted,
one.
it's just like 3 over, yep.
This one.
No worries.
Skip to step 7. Sorry, it's a long equation to plug
No worries.
in. And then so from that, after doing all the algebra and plugging to the calculator. Oops,
Let me see. I think you just bumped on the side there with the
Sorry.
paper. No worries.
I think, is it that one?
Yep, there you go. Yeah, your paper actually will, it's so sensitive, it actually can make it do things too.
And then from that, we got the initial velocity of 117 rad per second.
Neat.
Oh, sorry.
Okay, for part B, can we like erase this part? or move this?
We can scroll down a little bit to keep more space.
Yeah. Yeah.
There you go.
So for part B, we use the angular rotational equations. And then converted it to the. So then you just plug in for T.
Good. So just using those kinematics equations and using some substitutions to make them work. Any questions on number 10? Nicely done. All right, last one. We got the well question. Bucket in a well. They had a chance to go ahead and write theirs up already, so we can just have them talk through.
Good face.
Sig figs, slide those in here. Ah, that's not black. So we realized after we did this, there's a way easier way to do it, but I'll show you our way, and then Cade will show you the better way. So the context, there's a well and there's a crankshaft that's 0.4 meters in diameter and a shaft with a rope on it that's 0.1 meters in diameter. And we have to find the speed of the bucket going down if the tangential velocity of the crank is 1.2 meters per second. So you can see our diagram here, we're trying to find that velocity. And we know that the period equals 2 pi r over v. So if you plug in pi or r and v for the crankshaft, you get 2 pi over 3 seconds for the period. And then you can plug it into that same equation, only with the 0.1 meters and the period, and then v for variable, and you get 0.3 meters per second with 3 sig figs.
The only thing I would say is because of the way it went in, it worked okay. But you actually, it looks like you put in the diameter, not the radius, right?
Oh, yeah.
So for this,
Oh,
because,
yeah.
because you did both of them as diameter, it ends up kind of canceling each other out because you would just be dividing them both by 2. So, but if you use a different form of equations, then it may not do that.
Yeah.
So just keeping in mind that
So it should be. Great. Like that.
And the way that is significantly easier,
You may scroll it up for you.
yes, please.
Yeah, you can actually do it yourself, but it's a little bit easier with the
Oh,
mouse
okay.
than it is on the screen, so.
Because the crank and the shaft with the rope are connected, they'll have the same angular velocity. So we can find the angular velocity by just getting the velocity and dividing it by the radius. And sorry, I can't see the.
Oh.
Oh, yeah, that's such a small problem.
Yeah,
So and then now that you know the angular velocity, you can just find the velocity of the shaft by multiplying it with the radius, which is and then you get the answer, which is 0.3.
so both ways work. That second way is just using that V equals R omega. And like they said, recognizing the omega for both will be the same because they're connected. So when the crankshaft goes around once, so does the shaft itself. So knowing that, oh, their omegas are equal, find the omega for one, you know the omega for the other. So
Also, one more thing, we noticed that since the diameter of the shaft is 1/4 diameter of the crank, you can just get the velocity divided by 4.
yeah,
Epic.
yeah, 3 ways to solve this one.
Yeah.
Got 3 for 1 on that one. Good. Any questions on number 13? All right, nicely done by all the groups. So what we're going to wrap up with here is I do want to go back to our notes and talk a little bit more about torque, and especially a little bit more about rotational inertia. And we left off here, right? This is where we were at the end of the time last time, right? So we were talking about how with something just moving in a straight line, the linear motion, the inertia is only based on the mass alone. But when something is rotating, it matters where the mass is. So we had our sword fight thing over here where we're thinking about, oh, if I hold the end with all the weight, then it's easy to rotate. But if I put the weight out on the other end, it's hard to rotate, even though I didn't change the weight at all. I didn't change the mass at all. So for something rotating, it's not just the mass, but how the mass is divided up or how the mass is spread out. And so another way to think through that is if we look at the side on the left, and if we're given these objects, so like a barbell with weights on the end versus a barbell with weights squeezed towards the middle, if I'm just moving that in a straight line force across the weight room, it doesn't really matter where the weights are. I'm moving it in a straight line, so it's going to be the same whether the weights are in the middle or whether the weights are on the ends. It doesn't really make a difference. However, if I'm trying to rotate them, then it makes a difference because now the rotational inertia isn't just based on mass, it's also based on the positioning of the mass. So if I take it back to the linear side here, if I use a straight line force, then the distribution of the mass doesn't matter. But if I'm rotating it, the distribution of the mass does matter. And we're going to give you a chance to try it if you'd like. Now, you don't have to. Obviously, if you're in the Zoom group, you won't be able to try it here, but you can set up your, if you have a barbell or a dumbbell or anything at home, you could try it yourself. So if you want to try it, since multiples of you may want to, that's fine. Just use a paper towel so that I don't have to wipe it off between every person. So what I have here for you guys in the Zoom is I put a weight on each end of this. So just keep manipulating these meter sticks. And so there's one. And so you can grab it in the middle and feel how that is to spin. And then this one, I put 2 weights. So it has the same amount of mass. I just put them both in the middle. And so you can grab it here to spin. So any of you that want to try, just grab a paper towel.
Oh,
You can
yeah.
come up two at a time because one can try the heavy one can try the light one, and you can see the difference in how it feels.
Now this will be epic.
Like I said, if you are at home and you have dumbbells or barbells, then you can just simulate it yourself. Or
down?
if you have like
Down
some
the
kind of
pipe real
a
quick.
dowel rod or something, and you have some Play-Doh, you could put some Play-Doh on the ends of the dowel rod and put
Oh,
the
man.
same amount of Play-Doh in the
This
middle,
exchange.
and you could feel it as well.
Gracias. Oh man, I should do that one.
So to move it straight
Oh
across,
man,
to move it straight doesn't make a difference, but to rotate it, you can definitely feel a difference.
Rotation. Okay. All right, who wants to rotate this
I
one?
would like to rotate it. Oh.
See if I can do a trick shot here.
Oh man, you got close.
Really close.
I got you.
Need some help on my dude perfect.
I can't even do it.
Definitely takes some torque, doesn't it?
Hey, a quick workout?
Yeah, anybody else that wants to try, you can, or you can do it on the way out today when we're done, but you can definitely feel the difference when you're spinning it with the weights on the end versus the weights in the middle.
Watch the owl.
The owl's in
Right.
It's gonna like fly off in the street.
All right. So, there we go. Next thing we need to understand is how do we calculate that I value and take into account both the mass and how the mass is distributed? And so there's, for an object that is small enough to be considered a point, there is an equation, and it is just m times r squared. And we're not going to go through a geometric proof to figure out why that works for this one, just for sake of time. But what I want to say is this formula mr squared only works if they're considering it to be a pretty small object like a golf ball that has the mass evenly distributed. So something bigger like a bowling ball, they probably would give you a different formula. It has to be pretty small and the mass has to be evenly distributed for mr squared to work. And we'll talk about other examples here in just a few minutes. But here we're saying it says it's a particle, a very small object. So as long as it's small enough, then we can treat it as a particle, even though that particle is going through a rotational motion, and we can use mr squared. But the point they're trying to make on this slide is that if we take a value where we have a 2 kilogram mass that is rotating around a radial distance of 4 meters, using that mr squared shows us that our rotational inertia would be 32 kilogram meters squared. And it is a kind of an unusual and funky unit. But we have to take into account both the mass and the positioning of the mass. So that makes sense that there's both kilograms and meters in the unit. And you can see that the positioning of the mass actually bears greater impact on the inertia than the mass itself, right? We learned that here because these two things both have the same mass roughly, but their rotations are significantly different because of where the mass is. All right, if we look at another example where we still have a 2 kilogram object, same mass, but now we've reduced the radial distance from the axis of rotation in half, we can see that it doesn't just cut it in half, it actually cuts the rotational inertia to 1/4. Instead of being 32 kilogram meters squared, it's now only 8 kilogram meters squared. So if we cut the radius in half, we have a 4 times smaller rotational inertia. And so just recognizing that relationship, it would be 4 times more difficult to accelerate object A than it would be to accelerate object B, even though they both have the same mass. So like this, these have the same mass, but their radius is way different. So it's much harder to accelerate the one that has the masses out on the edge, and much easier to accelerate the one that has most of the mass in the middle. Questions on that? All right.
is that why like whenever you do like a cannonball, it makes a bigger splash than like just like flopping into a pool?
I don't
'Cause
think
you're
that has
kinda
so
like-
much to do with the
You're
rotation.
kind of like
That's
making a
just
center.
buoyancy.
Yeah, that's a little bit different concept, but yeah. Jeff.
Okay, sure.
So in this next section, it says, how would we find the I value if we had a collection of very small particles? So If we had three different particles and they were all rotating on the same, or they were connected and all rotating, we can actually, just like we do with other measurements, find the rotational inertia for each one and just add them together. So if we look at the first object with only 1 kilogram of mass at a 3 meter radius, we can use the mr squared value to find its I. And then for the 2 kilogram mass at 6 meters radius, we can find its value for I. And then for the 2 or 4 kilogram mass at a 2 meter radius, we can find its value for I and just add them together. They're all going to be considered small objects, so we use mr squared for each one. And if we just plug the numbers in, the mass for each one with its corresponding radial distance, and make sure we square the radius in each case, since it's mr squared, we can see that the first object that was a 1 kilogram mass only has 9 kilogram meters squared of rotational inertia. So it would be the easiest of the three to rotate if it was by itself. And then the middle one, the 2 kilogram mass, because it has such a large radial distance from the center, it would have the largest rotational inertia. It would be the hardest one to rotate by itself. And then for the one that's a 4 kilogram mass, even though it's the heaviest one, it has the smallest radius. And so it's somewhere in the middle of only having a 16 kilogram meters squared in terms of how much we would have to, or how difficult it would be to accelerate that one.
So does it generally, for calculating the inertia, does it generally affect the inertia more of the radius than the mass pretty much always?
Yeah, it will always, because we're always going to be square on the radius. And even when we adjust it for different shapes, that mr squared part stays the same. All we're going to adjust is just putting a fraction in front of it. And that's actually what we're going to talk about next. So once we find the rotational inertia for each of the three pieces, we just literally add them together. They all have the same units. They're all connected to the same axis of rotation. And so for this entire system of three different particles, it would actually have a rotational inertia in total of 97 kilogram meters squared. So if we could rotate any of them individually, it would be easier than rotating them all of them collectively.
That'd be a really interesting system.
Yeah. Any questions about that example? All right. So if we look at different shapes, if you have a hoop where all the mass is on the outer edge, but the center has no mass, that actually ends up being the same equation, mr squared. But if you have a disk where some of the mass is out on the outer edge, but some of it's more in the middle, and we're assuming that this disk is evenly distributed, if you have a disk, it ends up only being half of the mr squared value, because a lot more of the mass is moved in towards the center. And then if you have a sphere, it's just ever so slightly even less than that. It's only 2/5 of the mr squared. And there's other shapes as well. So these are the three primary shapes you might see. Now, you don't actually have to memorize these fractions. They're not on the AP list, but they don't expect you to know them. They'll tell you in the question what it is. So they'll say something like, on a disk where I equals 1/2 mr squared, or on a solid sphere where I equals 2/5 mr squared. And it's different if it's a solid sphere or a hollow sphere. So there's others beyond this. These are just some of the more common examples. If you're looking at a shape that is a rod shape, or even something like a meter stick, it's not, not round like we usually think of with a rod, but something like this. If you are rotating it from the center, instead of using the radial distance, we actually use the entire length. And so it's the mass of this times the entire length squared. But if I'm twisting it from the distance, or from the middle, that's pretty easy. And that's only 1/12 of ml squared, m times the length squared. But if I rotate it from the end, that takes a lot more torque for me to try to spin that from the end. Okay. And so it's actually 4 times harder. So instead of 1/12, it's 1/3. It's much more difficult to get that one to accelerate than in the middle.
Because you doubled the radius and then you squared the radius of like the circular thing. And so now it's 1/4.
Exactly. Yeah. So those formulas, again, you don't have to memorize them. You can actually even try this. You might be able to feel it even with the pencil. I mean, grabbing your pencil in the middle and grabbing your pencil on the end, it may not have enough mass to really feel a big difference. But if you have like a meter stick, you can actually feel it pretty strongly, the difference between wiggling it in the middle and wiggling at the end. All right, so how does torque connect to this idea of rotational inertia? Well, there's another formula. And what I hope you'll notice is, as we talk about what each of these variables means, what is torque most directly connected to that we talked about before we were looking at circular and rotational movement? Force. So even though they're not just directly interchangeable, torque is like force. There's a connection, right? And then what is I like? I is that rotational inertia. What if it's not rotating? What's the inertia based on? Just the mass. And then what is the alpha? Acceleration. So this is like F equals ma, but for rotation. Okay, force causes a torque, and it will be limited by the inertia of the object. But for something rotating, it's not just the mass, it's the mass and the radius factored in. And it will create an acceleration. But it'll be an angular acceleration of rotation instead of a linear acceleration. So a lot of times you'll see this called Newton's second law of rotation, because it actually is correlation to Newton's second law. Now I want you to look at the picture closely. If we apply an external torque on this weird shaped object, it is going to accelerate as long as I'm applying that torque. Similar to if I apply a force to an object, it will accelerate as long as I apply a force. It'll just be an angular acceleration here instead of linear. If I apply a force, it'll accelerate. What happens when I quit applying the force?
It stops accelerating.
It stops accelerating and moves at a constant velocity, right? Same thing's going to be true here. As long as I apply the torque, it will speed up and accelerate. But as soon as I quit applying the torque, it won't stop moving. It'll just keep going at that constant rate of rotation. So the same principles apply, but we're talking about different variables with different units and slightly different meaning, but a lot of overlap conceptually. All right, so if you look at the picture and watch the animation here, I might show it a couple times, but as we apply the torque, or apply a force which creates torque, it will spin. And you kind of have to see this one a couple times, so it's pretty quick. But you'll notice at the bottom, if I go back for a second, at the bottom here, it says the net torque is 0, so therefore the acceleration is 0. When I click it and we apply a force which creates torque, you can see it's got that green acceleration. But as soon as the force goes away, the torque goes away. And as soon as the torque goes away, now it's got a constant velocity with no acceleration. So I'll show you one more time.
What's the EXT mean?
External.
Oh, okay.
Yeah, but I would generally write it as net instead of external. But yeah, I'm not really sure why they're focusing on that word here. But so again, if I apply the force, you can see down at the bottom, it says the net torque is not 0, therefore the acceleration is not 0. But as soon as that force goes away, as soon as that force goes away, then they go back to being 0 again. So the force creates the torque, and the torque creates the angular acceleration. All right, questions about that? So here is the actual Newton's second law in rotational form with the units and everything kind of summarized. And this one actually is on the formula list, but it's solved for alpha. So instead of being tau equals I alpha, it's alpha equals tau over I.
Oh, there it is.
Yeah, you found it. And it actually shows it as sigma tau, and then it shows it as tau net. So it shows it two ways, but it's really this equation just in a slightly different algebraic form, just solved for alpha instead. But you do need to remember that torque's units, like we learned last time, are Newton meters, and that the rotational inertia that we focused on today is in kilogram meters squared, and that the acceleration, because it's angular or rotational in nature, would be radians per second squared instead of meters per second squared. So anytime you create, or anytime you generate an external torque or a net torque because you've applied a force, it will cause rotational acceleration. And like we said, this one is often called Newton's second law for rotational motion, because if you correlate it, it's like F equals ma. It's just that we don't think about mass alone. We think about both the mass and the radius for the inertia. And we think about angular acceleration instead of linear. And we think about the torque that the force causes. All right, so let's end up with a simple, reasonably simple question. I guess compared to some other things you might see, it's not super simple if you think about all these new letters and all these new meanings. But if we have this disk and it has a 2-meter radius and a 4-kilogram mass, and we apply a force of 5 newtons on the surface. So if I push on the surface, I'm pushing tangent to the circle. So that force is tangent to the circle, which means it is perpendicular to the line that goes to the middle, right? Perpendicular to the radius at that point. So this force is perpendicular to that lever arm, basically. You follow me there? Since it's tangent to the circle, if we drew a line from this red dot straight to the center of the disk, it would be perpendicular to the force I'm applying. All right, so we know that this equation here, this Newton's second law of rotation, is torque equals inertia times angular acceleration. Torque is Fr sine theta. We learned that last time. The force times the length of the lever arm times the sine of the angle that we're pushing the force with or applying the force with. And then now we know that I has some form of mr squared. And they're actually just telling us, because again, they aren't going to make you memorize it. For a disk, it's 1/2 mr squared. And so they're giving us that formula of 1/2 mr squared for the I value. And if we think about all the things we know, we can rearrange and solve. They want us to find the alpha. So this step might be not truly apparent right off the bat, but if you look at, there's an r on the left and there's an r squared on the right in there. So if you divide both sides by r, you get that, right? There's simplifying a bit. And then if you isolate the alpha, you have to multiply both sides by 2 to cancel the 1/2, divide both sides by mr to get the alpha by itself. And we can find the angular acceleration would be 2 times the force times the sine of the theta, which is going to be 90 degrees. It's tangent to the circle, over the mass times the radius. And we know both of those values as well. So we can plug everything in that we know and find out that the acceleration would be 10 newtons over 8 kilogram meters, which is 1.25 radians per second squared in terms of angular acceleration.
I did 4 divided by 5. I mean, no, I did 5 divided by
4.
5 divided by 4, and I got that. Let's go.
Yes, that is how math
Multiple
works.
choice ready.
All right. So any questions about this example? Want to get one problem in where we're solving this kind of a scenario.
Wait, why did the radius not be squared?
Well, it is here, but we've got radius here and radius squared there. So when we divide both sides by r, it simplifies. Any other questions? All right, so in the end, that acceleration, we can look at the diagram and see that if I apply a force to that direction, it would make it spin counterclockwise. All right, we're not going to look at this one today because it will take us more than the 5 minutes we have left. So for you guys that are in the Zoom, if you have questions for me, feel free to stick around and I'll chat with you once we get these guys dismissed here in a few minutes. But if you don't have questions, you can be dismissed and I'll see you on Tuesday.
Thank you.
Thank you.
All right, for you guys, just once you're got your area kind of cleaned up and ready, I'll just spray them down the tables and you can wipe them off.
Yes, sir. Speed.
Yeah, once you've cleaned off your table surface, you can leave a couple minutes early, get ahead and start on lunch.
Thanks. What is the disinfectant?
It's got alcohol in it, but
Sodium hypochlorite.
there's hydrogen peroxide, some alcohol, I think.
Bleach.
Smells kind of like Windows.
It does kind of smell like
Corrected
Windex.
by the question.
Or that's just Oaks Windex. Thank you.
Thank
You're welcome. See you guys.
Mr. Webb. Have a good one.
Enjoy your day. So Johnny, how many people are on the Oaks News staff?
We have, I think, 8 or just 9 kids this year.
Okay. Is it actually a class or is it more like an extracurricular?
Yeah, it's an elective, but we actually have a class with Mr. Chobanian on D-Days.
Okay.
Yeah.
You can.
Bye, thank you.
You're welcome. Have a good day.